Welcome, everybody. Thanks for joining us. Today we are talking about plastic staking. This is the ultimate plastic staking webinar. I am Jason Dornbos. I am a sales manager here at Xtol, and I've been here for almost 15 years. And with me today is
Sasha Becker. I've been here for 4 years now, applications engineer. Work with the staking products almost on a daily basis.
And if you're just joining us, we use the chat function in Teams so that you guys can interact with us. We try to make our webinars as interactive and engaging as possible. So as questions come up, please send them in via the chat. We will do our best to answer those questions and address those things in the moment. So when you send it in, we will try to finish our thought and answer your question, because if you're like me, if I have a question burning in my mind, I no longer can take on new information. So we want to make sure all the questions get answered as much as possible. And so we want this to be a back and forth. We also can go deeper into certain areas if there's lots of questions about certain things. So please make this webinar your own and ask lots of questions. If there's certain really detailed specific things about your application that you want to ask, you can even say that in the chat that you want to talk about your specific application, and then we know that we can follow up with you after the call to dive into that. So with that, everybody get your hands on your keyboards, get ready, because the first slide is about you. Why did you join this webinar? I want to know, do you have problems with plastic staking? Never heard of it before? Do you have a project that you're working on that's going to need plastic staking? Are you confused and thought this was going to be about plastic welding? All right, so we got some need update on current technologies. Good. Yep. Some general information about plastic staking is good. What else? Why did you guys join this webinar? Refresher on staking. To really learn the lingo for plastic staking. Oh, that's good. Yep. Looking for other opportunities. What else? Bettering our PM strategies. Keeping up with the latest tech. Not familiar with the topic. Thinking about implementing it on design. Never tried it. Okay, great. Good. Need more experience on how to optimize heat stakes. New project. New technologies. To increase the process knowledge. Faster cycle times. Learn more about it. Great. All really, really good reasons. And we should be able to dive into most of this stuff. Let me give you a quick overview of who Xtol is so you can see how plastic staking fits into our expertise. Xtol exists to solve complex plastic manufacturing challenges. If you look at our logo, there is a square with two lines crossing over it. It's sort of like a graph. On one side, there's plastic welding expertise. On the other side is custom automation expertise. We find that plastic welding providers don't do very well with custom solutions. So whatever your application is, it needs to fit inside of that box that they build. On the other side, custom machine builders lack plastic welding expertise. They can tailor a solution around your application, but they lack the welding expertise to deliver a high-performing solution. Xtol is the best of. You get a configurable plastic welding solution that's optimized for performance. So we have three main areas where we can assist you. We have engineering services, plastic assembly technology, and custom automation. Those break down like this. We can help you with 3D printing. We can help you develop your joint design, and we can help you do prototype testing and trials to make sure that the joint design you've selected is going to be sufficient. We can help you do tests to validate the strength. And if you're doing welding and you need to leak test things, or there's all kinds of different testing we do. The main goal of our engineering services is to partner with you to help you have a robust manufacturing process when you get to that point. In the center here is the plastic assembly technology that we work with. So today we're going to be talking about staking. That's these two technologies right here, InfraStake and nanoSTAKE. The other technologies that are listed up here are all welding technologies. And we'll dive into the difference between staking and welding. And then custom automation. We make fully custom automation machines. We make automatic machines that you never have to touch the parts. semi-automatic machines where there's some operator interaction, but there's a lot of automated components inside. Standalone machines where an operator loads the machine with parts, it does whatever operation on those parts, and then they take the parts off. And then we also can offer our plastic assembly technologies as integration packages. So you buy the components you need, and then you build the machine yourself. Or maybe you have a machine builder you are familiar with working with, and you want them to build the machine for you. They can buy integration from us and build the machine. All right. That's our topic for today, InfraStake and nanoSTAKE. So on a scale from 1 to 10, just put the number in the chat. How would you rate your plastic staking knowledge? 1 is, what is plastic staking? I've never used it before. 10 is, I could give this presentation. Okay, 3, 8, 8 and 9. Woo, that's pretty good. 2, 5, 2, 5, 6, 7, 8, 5, 6, 10. Sash, oh, you are giving this presentation. Nice. 3, 6, 3, 3. Good.
Pretty suspect if I.
So there's a range of people's experience between, you know, very unfamiliar to high level.
Good.
That's good stuff. Thank you, everybody. So here's a quick run through of the various staking technologies, and then we'll dive in. But before I talk about the staking technologies, let's explain the difference between welding and staking. Welding is when you take two plastic components and you're bonding them together chemically. Molecular bonds are happening between this component and this component. Staking is kind of like a plastic rivet. It's a mechanical retention. So here you might not even have two plastic components. You might have one plastic component. It's got a boss on it, something standing tall. And then the other component has a hole or some type of a mating interface. The boss goes through the hole, and then you form the top that's coming through to capture that mating component. So that mating component could be another plastic part. It could be a printed circuit board. It could be a metal bracket. It could be a whole lot of different things, but you're forming a head over top of that mating hole to capture it and keep them together. So some different staking technologies. And yes, Scott, this presentation will be available after the webinar. First off, hot punch. That's the one on the left here. Basically, you have a heated tool, and this top little graphic part of it is meant to be like indicate like a resistance heater or something like that wrapped around a metal tool. That heated tool is meant to touch off on the top of the boss, heat, and form it. There's ultrasonic staking. So ultrasonic uses, a lot of people are pretty familiar with ultrasonics. It's vibratory energy. So the horn is actually vibrating up and down, very, very small amount, but it's doing it really, really fast. And that vibratory energy melts the plastic and forms it into a stake. Hot air is just like it sounds. You have a cartridge that is heating the air that's blowing through the module. That very, very hot air is being blown onto the plastic boss, and that softens it. So then the forming tool comes down and forms it into a stake. InfraStake uses focused infrared energy coming off of a bulb to heat the plastic boss and then form it with a non-heated forming tool. And nanoSTAKE uses a smart respond heating system that heats a small heater to a very precise temperature, forms the plastic boss, and then cools before it retracts. Can it be waterproof? So staking is not usually considered waterproof. If you had a hollow boss and you were filling something and then you staked that hollow boss shut, that would be a hermetic seal. But usually you're not, if you're going to bond one component to another, you would have to have some kind of a gasket between those components. And then when you stake them, you're trapping the gasket, which creates the hermetic seal. Is InfraStake slower or faster than other staking technologies? That is a great question. We'll show a couple of videos. Generally speaking, InfraStake is kind of middle of the road as far as speed, but it kind of depends if you have a lot of stake points or few. If you're talking about one-to-one, one stake point is going to be fastest with ultrasonic because that can form that plastic boss really, really quickly. But ultrasonics, you typically would have one ultrasonic horn due to the cost of a generator. You'd have one horn staking one after another parts. And so sometimes ultrasonics end up being slower because there's lots of stake points. Whereas InfraStake, nanoSTAKE, actually all of these other technologies other than ultrasonic, you'd stake all of those bosses simultaneously. This is another, what grade do you learn the forms of heat transfer? So hopefully this is review for most of you, but there are three modes of heat transfer: conduction, convection, and radiation. Conduction is heat transfer between two solid bodies. So you have this piece of butter going into a hot pan. The pan is conducting heat into the butter because it's touching it. Convection is heat transfer through a fluid body. So that is like air. In this little GIF, you can see the guy being like blown by the wind. He's being cooled down by the wind because the wind is blowing. Well, convection can work the other way. You can have the wind be hot and that would heat something up. And that's what hot air uses. Radiation, that's what InfraStake is using. It's like what you feel when you're standing in front of a fire. Flames generate heat. And when you're standing in front of the fire, you feel that warmth on the side of you that's facing that. If you turn, immediately you feel that heat on the back of you. You also feel radiation when you're standing out in the sunlight. That's radiation. It's electromagnetic waves emitting and causing the heat to be absorbed. What's this question here? Usually InfraStake provides its own clamping between the two parts. Yes, it does. Correct. And we'll get into that even more. Yep. Sasha,
great.
Take it away.
All right. Thanks, Jason. Yeah, so we'll jump right into radiative heat transfer in the form of our InfraStake technology, as Jason mentioned. So I'll play a quick video for you so we can just see a cycle. And there it is.
So 9 seconds for that sample part.
Not too bad. For 4 stakes, pretty good.
Yep.
So David, that's a great segue, your statement there, into what I'm about to talk about. So in case you weren't looking for it, you probably missed that the first step in the process is to clamp the components together. With the nanoSTAKE technology, we're able to clamp both plastic components via this yellow figure here, which is the concentrator. So that comes over, fits over the boss, clamping the two components together. Once clamped, the lamp comes on, and this concentrator acts as a reflective surface as well. So it reflects all that light energy to the entire surface of the boss. So we're not heating just the top of it. We're not heating the bottom of it. We're not spreading that heat away from where we want it. So we heat that boss efficiently. You'll notice too, we have a couple blue arrows here that are denoting some cooling air. During the heating process, we do have a low flow cooling air coming through the module. And that's meant to just expel any gases that may be released from heating the resin. So that's going to eliminate any type of thermal event or flare up. So once everything's sufficiently heated, we have this cold forming tool, which we call a punch. As soon as that lamp turns off, the punch fires, forming that boss. And then you'll notice we do have some more of these cooling lines here. This is a high flow cooling air. So that's meant to cool the entire, this entire cavity. So it'll cool the concentrator, it'll cool the punch, and importantly, it'll cool the resin to form that boss. So once sufficiently cooled, it retracts and we have a perfectly formed stake. We got another comment here.
Yeah, great solution for flat surfaces. The true test is when you have tight, deep spaces to get into. Concentrator size becomes an issue. Continual challenge for us. Yes,
that's fair.
That's something that we'll talk about is how to get the InfraStake down into some pockets and stuff.
Okay. So as you can imagine, with the radiative heat transfer, the color of your material is going to be a very important decision. As we're showing in this graphic here, and we can all tell when we wear a black shirt on a sunny day versus a white shirt, we tend to absorb more heat with the black. So the same thing is going to happen to your boss. So that's not to say we can't stake a white boss, because we certainly can, but cycle time is going to differ from white to black. Typically we see a lot of black materials or light gray or gray materials.
And yes, orange would definitely work. Yep.
Okay. So we use a kind of a broad spectrum bulb to heat. So we do have, we're hanging out mostly in this infrared area, but we do have some visible light, as you could see from the from that video that we showed. We actually use a bulb that we all use every single day. Does anybody have an idea of what a good bulb would be to use in the InfraStake module?
Pop quiz.
You use it every single day.
Assuming you.
Yeah, I guess
most people,
there's an exception.
Yes.
Hey, halogen, thank you. Yep. So it's just a tungsten halogen lamp. And depending on what module type you are using, you're either going to have a 100-watt lamp or a 35-watt lamp. And these are very similar to the non-LED headlamps in your car.
Yep.
Okay, so that first video we showed, I guess, doesn't fully, pass along the idea that we're not using convection, we're not using conduction. So this video here kind of captures, and I think shows very well, that we are heating that boss through radiative means 100%. So I'll go ahead and roll it for you. So that's Jason again, I believe.
Mm-hmm.
So what he did is put a sample plaque on there, took that concentrator off the module and just set it over the boss, turn the lamp on, and you can see that boss is soft enough to form by hand.
So we created an air gap, plus the punch was not the one that was in the module, it was a different punch, so it wasn't inside the whole heating, so we're not heating that punch up either.
So pretty cool video, I think, to show that it is IR radiation. Okay, so just kind of to conclude with some InfraStake benefits, we are softening the boss before staking, so we're allowing that material to flow easily, which minimizes internal stresses, which allows us to get strong stake joints. The modules themselves clamp the workpiece together independently, applying that independent pressure right over the stake. So we do create tight joints with that. We're also monitoring a couple parameters that ensure quality and consistent parts. And because we are, we're not vibrating, we're directing the heat where it's needed. We're not overheating things. This is a safe technology for electronics or other sensitive components. The InfraStake heats the boss without touching it and forms it with a cold punch. So therefore, we don't have really any sticking associated with this technology. It also uses low wattage bulb. So we have low energy consumption. We're directing that heat to the boss, to the intended surfaces, and we're not overheating it, so we're not getting read through on any A surfaces. And because it's staked together, any assembly that is assembled using this technology you can't really open it without destroying it or damaging the stakes. So it is tamper evident in that case.
Kevin mentioned that they see some sticking. So you must be using, I guess you're using InfraStake. So if you're seeing sticking, typically there's a couple potential reasons for that. One would be if the cooling time, the punch time, isn't long enough, or the cooling airflow isn't high enough. That can, if you can imagine, cycle after cycle, that punch is coming in contact with a very hot plastic, and that can cause the punch to get too hot. And if the punch is really, really hot, then it could start to stick. Another potential reason would be if there's scarring on the inside of that punch. Mm-hmm. Basically, if you've started to stick and now somebody takes a metal tool and digs out the plastic out of the punch, that can create grooves that will make it want to stick to the plastic more. So usually, if that starts, you want to maybe get a fresh punch and make sure that your cooling time and your cooling airflow rates are high enough so that the punch, when it's at its steady state, isn't hot enough to start to stick to the plastic. Some other questions are coming in.
Are some materials better than others as far as fumes coating the concentrator lens? So if they're processed, we shouldn't have, I guess, visible fumes for sure. I imagine some nylons could have a little bit of fumes that are going to coat it. We typically recommend we do just, include that in our PM schedule of just kind of wiping out that concentrator with a cotton rag or something like that, just to clean it. That's typically all we need.
Yep. What makes this joint the strongest? So the strength is because we are softening the parts before we form it, and so that allows all of the molecules inside of that plastic to be malleable. So when we form it, there's no internal stresses built up inside it. We're heating from the outside in, so the whole boss is softened. We form it, and we're holding it tight that whole time and allowing that punch to kind of create a pack out pressure. Similar to what you get when you're doing injection molding, the pack out contributes a lot to the strength of the part. The same thing is happening with InfraStake in the punch.
So Scott asks if the non-boss material melts too. I would say no.
Yeah.
But if we have a black mating component with, say, a white boss, the energy needed to heat that white boss is, pretty significant compared to what is needed to heat the black. So you might get a little bit of residual heating on the black, which would show up as, maybe a small shiny surface.
Oops. Didn't mean to do that reaction. Right. I'm trying to click. Other questions in here are, is there a matrix table that will be shared for cycle time variance based on color? We don't have that, so we can't really share that with you. Is there any shrink of the post to apply clamp force after cooling? So when we're designing our punches to the size of the boss, we always undersize the punch. So the punch is a little bit smaller of a cavity than the amount of material that's in the boss. That way, when we're staking, we always have the right amount of volume, and there should be a little bit of plastic that squeezes out the edge. That way, you're getting your pack pressure and you're not underforming the boss.
Black on black is okay, Scott.
Are there duty cycle limits? Boy, I don't know that answer off the top of my head. There is a limit. You don't want to finish staking and immediately start the next one over and over because not because the bulb is going to die or something like that. It's because the temperature of the module itself would start to warm up. Mm-hmm. Do you design in Flash for InfraStake? Yes. Another one here. Sam is answering that one. Which type is cost effective and more efficient? I'm wondering if you can clarify that question. Are you trying to figure out which staking technology is more cost effective? How much is diameter of the punch, min and max? Okay, so let's keep going because we're going to get into some of this stuff.
Take control.
I want to show some examples here. So this is a Honda solenoid cap, and originally this product was being staked using hot punch. So a hot metal tool comes down and stakes. There's 2 stake points. One, turn my laser pointer on. One's right here. One's in the back over here. It was forming those, and because it's a hot piece of metal that's doing the staking, it was actually heating up the entire part. And because it's a solenoid, the function of this device depends on the amount of resistance that you get in the coil that's wrapped around here. And it was actually the hot punch process was heating up the coil, and it was changing the resistance that was measured in testing. So the customer was having to wait 45 minutes after staking in order to be able to accurately measure the resistance. When we came along with InfraStake, we did some trials, and they measured the resistance immediately after staking the part using InfraStake, and they were able to get an accurate reading right away. So they were able to eliminate 45 minutes of WIP because they were able to go directly from staking to testing the resistance on the solenoid. That kind of illustrates how the InfraStake process is putting heat into the plastic boss and only into the plastic boss. It's not heating up the rest of the assembly. Is there a strength comparison data between IR, nano, and hot air? What do we have? Do we have some things that we can share? We have a yes, we'll get into that.
Yep. We can share something on that.
Okay, door panels. We stake quite a few automotive door panels with InfraStake. This application is something where the bosses are typically fairly tall for door panels because of the size of the component. In order to be able to nest all of these parts inside of each other, and there's often warp on injection molded parts, you need a fairly tall boss in order to find the holes for staking. So InfraStake was able to stake these. The bosses were extra tall. We have different designs for all these different concentrators to allow us to stake all these different sized geometries. And this particular one had 35 bosses on it. So all 35 were staked in 15 seconds, 10 plus 5. And that was allowing the customer to move a lot faster than if they had used ultrasonic and had to stake point by point.
I think that's a great example of how configurable the InfraStake technology is.
Yeah. Okay, so here's the BMW engine cover. Sorry that it was frozen for everybody. I don't know why that was happening. This, as I was trying to explain, the backside that we're looking at is the part where the staking is happening, but it's not the part that you see when you open up the hood. And so we wanted to make sure that the A surface didn't get scratched or marred or show any read through. InfraStake works really, really well for that. The other interesting part about this application is that there's lots of different configurations of bosses. So you can see some of these bosses are taller than others. Some of them are different shapes like tabs and all close together. And InfraStake was able to do all of these, all 54 bosses in 10 seconds, essentially. Are there any questions other than the frozen part? Nope. Okay. Banner light curtains. So this is a great application here. So can anybody spot the stake?
Might be frozen again.
Oh my goodness.
Yeah.
All right, you take control.
Okay.
Go to the next slide. Perfect.
There we go.
Can anybody spot the stake on this light curtain module? Yes, no? It's right there in the top right corner. You can see the kind of the row of 1, 2, 3, 4, 5, 8 little I don't know what they call on a light curtain, the thing that's actually doing the light curtain function. There's a stake point right there where the mouse is. And there's actually another one kind of underneath the blue section. InfraStake was able to stake the part so cleanly that it looks like it's a molded in component. In this particular one, we were staking the front part of the assembly together, and then the back side has a printed circuit board that was being staked on as well. What is deemed a standard concentrator size type? We have many of these units on the floor, but the angle of the concentrator seems to change from job to job. The boss size design are basically the same on our products. Which should we stick to? Okay, we will address that. This is we'll show a slide that shows the different concentrators that are standard versus what we consider modified. And this particular example here would have had a modified concentrator and a modified punch. Because if you look at that stake point right in the center, that's right by those wires, that's not an ideal place to put a plastic stake. The wires could become desoldered if you were using some other technologies. With InfraStake, we were able to modify the one side of the concentrator so only the side that's closest to us was receiving the energy. And then the punch was basically half of a punch that would only form half of the boss. That way, the wires were able to still stay soldered and not malfunction. And then there was a question about the concentrators. So these are some standard InfraStake concentrators. There's different sized modules, IS32, IS125, ISM20. There's 3 different sizes for IS32, and the nomenclature here is indicating the size of the aperture. This is the opening at the end of the concentrator. We basically use different sized concentrators for different sized bosses. It's something that we would help you figure out. It's not something that you have to figure out which concentrator do I need. Our team looks at your design. We figure out what concentrator will work best for it. And then we also custom design the punch so that it's the right exact size for your application. Now, when I say modified concentrators, that's what a modified concentrator looks like. It means we've taken a standard one and modified it. We've cut a portion of it out. Sometimes we leave those cut out portions open. Sometimes we can weld in what we call a closeout to shut that portion off. And I would say at least half of the InfraStake modules that we produce have a modified or custom concentrator of some kind. Are there any questions about that?
Well, I wanted to come back around to Kevin's question. He said that the angle of the concentrator seems to change from job to job, even though the bosses are basically same size, same design. Typically, if we see an angled concentrator or angled module, that's to avoid some other interference, some other part feature. That may be the case for you. If it's not, we'd love to talk more offline and dive a little bit deeper into what you're seeing.
Okay.
So he said sometimes it's due to space. Yes.
Yeah. All right. nanoSTAKE. So should we play the video? Let's see how well it plays if we're sharing it like this. Unless there's the question that just came in.
No, I think someone has.
Okay. Somebody's trying to record.
Yeah.
Okay. This is the nanoSTAKE process. And what you'll notice is on the left-hand side is a thermal image of what's happening on the right. I'll play this more than once. Okay, so watch closely. You'll see the left-hand side. Notice just how small of an area is actually getting hot. It heats up from ambient. It's doing its staking, so it's at 200 degrees Celsius or something. And then it's cooling down to ambient, so much so that you can touch it. So every single cycle, it's doing that. Take it away.
Should we answer that question real quick?
Sure. What's the question?
I think it's probably asking how the cuts in those concentrators are affecting the heating of the pin.
Yes.
Fair question?
Fair question. So as you can imagine, this certain spot is not doing a good job reflecting any energy into the boss, right? So it just means that we aren't heating it as evenly as would be ideal if we had a complete concentrator. That said, You can actually get away with some pretty heavy modifications to the concentrator. It slows the process down.
Yep.
It shrinks your process window, but it still is a feasible solution. We've got lots and lots of applications out there in the world that are able to still stake parts.
We just jumped into the nanoSTAKE process. So you're probably going to have to just compartmentalize everything you were just told and learned about InfraStake process, as this process is completely different.
Totally different.
So for one, it's a conductive heating, as you saw in the video. So the first step here, we heat the punch up to a programmed temperature. Once there, we form that boss to a programmed height. Once we're there, we rapidly cool the entire module and the boss to some extent to a programmed release temperature, and then we retract the module with no sticking. So the biggest reason this was developed by Xtoll was due to the challenges of some LED applications and electronics, places where there's sensitive components that are tightly packed, where we just, quite frankly, couldn't fit an InfraStake module into. So we're able to rapidly heat this module up due to our Smart Respond heating technology. So what that is a low current heater. It's 1.5 amps to heat it up, and we're constantly monitoring temperature. So we're getting up to our set temp, steady state before we stake. We're also monitoring the punch position throughout the process. So it's really a closed loop process. So this graphic just kind of shows the steady state, that it is repeatable. So we start at, our room temp. We can ramp up if you want to go ahead and hit the graphic. We can ramp up to our melt temp, back down to our cool temp, back and forth. So it does keep it does keep the temperature process repeatable from part to part. This next graph shows 100 cycles. You can see the red dots at the top. That's our melt temperature. The blue ones at the bottom. That's our cool temperature. And over 100 cycles, we see very, very little difference in the actual temperature.
Which of the two processes require more maintenance? We're going to do a comparison of the processes at the end, but essentially, I would argue InfraStake requires more maintenance, right?
Yeah.
Because InfraStake, you're going to have to clean the concentrators on a regular basis, and then the lamp is a consumable, so that is something that after like 2,000 hours of on time, you'll expect the lamp. You have to replace the lamp, and it's pretty easy to do.
Yep.
Hari's asking about some issues that they're having with nanoSTAKE. We'll have to address that because I don't know the answer to that. We can get our service team involved. How many of these can you do at the same time? So nanoSTAKE and InfraStake, both we would do all of them simultaneously. So if you have 50 stake points in your application, we can stake all 50 all at the same time. How many cycles is the life of pins, and what maintenance is required, and at how many cycles? For nanoSTAKE, typically the reason why you'd have to replace a nanoSTAKE module is because the punch cavity has worn away, right? We're staking parts, and often there's some abrasive material inside the plastic, and the punch cavity does slowly get worn down. And then at some point, you'll have to replace that so that the punch cavity can be fresh again.
Yep.
What kind of heaters are those? Do you know what the kind of heaters are in the nanoSTAKE?
It is proprietary.
Proprietary. It's a special heater that can, it has embedded temperature sensing inside it. So that's how we're measuring the temperature of the punch. Can you control the height of the head where we can create a specific clearance to the part being trapped? Absolutely. So the punch cavity of both nanoSTAKE and of InfraStake is custom every time. So we can make the punch be the shape of a dome. We can make the punch be the shape of a rosette. We can make it more of a flattened top. We can make it wider, narrower. We can do whatever is required by the application. Those things might impact the strength, but we would work with you to figure out, okay, what's the ideal punch shape for your application to make sure it fits and also provides the adequate strength. What's the highest temperature that you can reach with staking technologies? Good question.
With the nanoSTAKE, it's upwards of 750 degrees F.
Okay.
But there is a time limit, I believe, which you'd want to run that. So
we have InfraStake working a lot better than nanoSTAKE at our facility. Okay. And do you recommend any coding on nanoSTAKE?
We do some hardened coatings. We do like to try a couple different things, kind of tailor it, to your needs if we can.
Yeah, if your material has anything abrasive inside of it, like a talc filler or a glass filler,
yeah.
Typically you would want to harden, when we would harden the tips of the nanoSTAKE modules to reduce the wearing that happens on those.
Can nanoSTAKE or InfraStake work on coated surfaces? We typically don't recommend that. We ask to mask all bosses if you're doing a paint or like a chroming or something like that. Especially if you have some kind of chrome surface, the InfraStake doesn't work well. It just reflects a lot of that energy. And then conversely with nanoSTAKE, you have to heat everything conductively, so that adds a little barrier to heating the resin.
What material are the nanoSTAKE tips?
They're just stainless steel.
Yeah.
Or we can coat them with a
hard coating.
like a nickel coating.
Yeah. NanoSTAKE compared to HeatStake. So when you say HeatStake, are you referring to what we have listed here as hot punch? Assuming that's the case, I think that's going to be a yes. Yes. So HeatStake, some people call it HeatStake, some people call it hot punch. In this technology, this entire punch is being heated to your operating temperature, 500 degrees Fahrenheit, something, maybe it's hotter than that, maybe it's a little colder than that, but it's being kept at an elevated temperature the whole time because it takes too long to heat this punch to that temperature. And then if you tried to cool it down between cycles, it wouldn't work. It would be too slow. NanoSTAKE is very different because we are heating from ambient to the operating temperature and then back down to ambient every single cycle. So when your machine's, like when you're running parts, every time you pause, take a break, it is sitting there at ambient temperature. You can reach in, you can touch the modules, they're cold to the touch. And then we're also monitoring all of these things way better. So we have a position sensor on the module that's measuring the final stake height. So we know, did we actually stake this boss all the way? We're also measuring the temperature. So we know we're at our operating temperature, and then when we've cooled it to a appropriate release temperature. So that's some of the differences between just traditional old school hot punch and the very sophisticated NanoSTAKE technology.
And to kind of just add to the cycle time of heating and cooling the hot punch. So with the NanoSTAKE technology, we're able to heat that punch up to, 250 C within a matter of, 2 or 3 seconds. And then cool it down, it'll probably take 4 seconds, maybe 5 seconds to cool. So it does happen very quickly.
Mm-hmm. Tell us about the wires.
Yeah, the wires. NanoSTAKE, it's easy to integrate. If you want to compare it to like impulse welding or impulse staking, where you have a current that impulses or pulses through your stake head there. If you're familiar with that, you've got big transformers, lots of power, lots of amperage. You got big, bulky wires. With the NanoSTAKE, we're using low current, so we've got 1.5 amps. which makes very manageable, wiring and connections and easy to integrate. That graphic on the right is actually an example of the size of wires that are connected to each nanoSTAKE module. So you can see the very small, very easy to manage.
Giant thumb in the picture.
Okay, yeah, so this was kind of what I was touching on how quick the process is to actually heat up, to stake, and then to cool again. So typical cycle time here, and this will depend on the size of your boss and things like that. But typically just a couple seconds to heat up, followed by, a couple more seconds to form the boss. And then your cool down time, is just a couple more seconds before releasing the boss or releasing the module.
Fits in tight spaces, I think, is a great way to answer that. If product design is not a consideration to select the process, which is considered to be best in terms of cost to performance?
It's a really good question.
I would say InfraStake. Cost-wise, InfraStake and nanoSTAKE are very, very similar. nanoSTAKE is slightly more expensive. InfraStake, as we were showing earlier, it produces the strongest stakes and the tightest stakes. So strongest because we're heating the whole boss before we form it, and tightest because we're clamping every single stake point independently with pressure to keep it tight throughout the process. nanoSTAKE does not have independent clamping. You have to have auxiliary clamps to clamp your parts together for nanoSTAKE. One of the main drivers that would drive you to use nanoSTAKE over InfraStake is what's on the screen right now, right?
Yep.
It fits in tight spaces. Yep.
So nanoSTAKE too, if you want to consider materials, the InfraStake probably does a better job with a wider range of materials.
Mm-hmm. Mm-hmm. Does the staking process loosen with thermal cycling? Ooh, that's a tough one. So I think what you're asking is, like, after you've staked your part, assuming your part goes through thermal cycles, in its regular use, does that allow the stake boss to relax over time? I don't know this for sure, but what my hypothesis is that InfraStake is going to do a better job of keeping that part tight because the molecules were softened and then reformed versus being forced into a position more aggressively. So there's no built-in stresses. The molecules are actually okay being where they are versus if they're forced into position, they might want to relax and not hold as tightly with other technologies. What do you think? Do you think they would be? Have you seen has anybody on this webinar seen examples of a staked joint loosening after thermal cycling when it's normal use? And while you're thinking about that, some other questions here. Do you have a comparison of process character as a decision matrix? We do have a plastic decision matrix on our website, and I can make a note to share that after the call. Plastic. What's the other questions that are in there? Anything?
A question about size of.
I don't have a tight space, but my boss is 2 millimeters. Is infrared compatible with such size? With InfraStake, we can certainly stake small bosses with InfraStake, but the proximity of mating other components and stuff like that does impact the ability of InfraStake to get into the situation. So you can check out actually, since I'm sharing the screen this way. Okay. This is the size of the modules right here. And as we've talked about, you can modify them to a degree, but you basically have a 32 millimeter diameter module on these two versions, and then a 20 millimeter diameter module over here. So if you have a wall next to your stake point, and it is 1 inch tall, and it is only a couple of millimeters away from your stake point, it might be tough to fit InfraStake down in there. There are things that we can do, and we would encourage you to send your CAD data to us so that we can review it for you and give you an analysis of whether or not it's feasible. If there's any design flexibility, we can help you redesign your parts so that they are compatible with InfraStake. And if there's not, then we would, there's certain things that we can do to the module to try to help it fit. But if it not, and there's other technologies that are a better situation, like nanoSTAKE, then we would steer you in that direction.
Yeah, there's a lot that goes into the decision. And as Jason mentioned, sending your CAD data for a feasibility study is kind of the first thing to go to, right? We'll do a free feasibility study for you. And if InfraStake doesn't work, we're going to look at nanoSTAKE. If nanoSTAKE doesn't work, we're going to tell you what we feel is the best route to take, even if it's not one of our technologies.
If you want to have access to these design guidelines, they are readily available on our website. So you can check out our website and go to the different technologies. There's InfraStake and nanoSTAKE technologies in here, and you can find the design guidelines there.
All right.
Benefits of nanoSTAKE.
Again, so we just kind of hammered that. Fits in the tight spaces that other technologies won't. Since it doesn't vibrate and, we're putting the heat where we want it to, it's safe for electronics or other things with, sensitive components on it. We've got low amperage, low wattage usage, so we have low energy consumption. Because we're not vibrating, we are making clean stakes without any type of particulate. Because we're monitoring both heat and position throughout, we're creating a very reliable and repeatable process. As with all staking applications, once your assembly staked, it's tamper evident because you need to destroy it to get it open. And again, because we're not introducing excess heat, we're putting it where we need to. We're not vibrating or anything like that. We don't get read through on any A surfaces or sensitive surfaces.
One of the questions was, would you expect any engineering thermoplastic material to be able to be joined using InfraStake? For example, PBT glass filled 25% with flame retardant in it. Yes, that material would work. Have we come across a material that doesn't work with InfraStake?
It all kind of depends on your cycle time expectation.
Yeah,
some take longer than others.
Yeah, higher melt temperatures. Some of the more challenging ones would be basically a clear part, which can be staked, but a clear part with a really high melt temperature and glass in it, like all these things that are trying to prevent the part from melting. We have to overcome all of that with whatever staking technology. What are the parameters I should validate for IR riveting? That's kind of that's a pretty open-ended question. I guess if you're trying to make sure you have a strong part, I think periodic tensile testing would be appropriate just to make sure that you're getting the strength that you need. But typically what we see with a machine that has staking is some way to monitor that and make sure that the stake was fully formed. So both InfraStake and nanoSTAKE have built-in quality control. So let's look at nanoSTAKE to start, since that's what we're on. So nanoSTAKE has this built-in position sensor, and it's got temperature monitoring. We can use this position sensor to measure the height of the boss before we stake it. And then it's part of the process that we measure the stake after we have formed it. If we know that there was a boss there to begin with, and the boss has now been reduced in height to a certain amount afterwards, we know we're producing a good stake every single time. On the flip side, the IS32 InfraStake has a built-in position sensor. The other two models, which are older revisions, we would put in a full stroke sensor has basically a switch that's measuring the position of the punch. This sensor can be used, again, to measure the height of the boss beforehand and then the final height of the stake afterwards. That tells you I had a boss, it was the right height to begin with. It wasn't a short shot. It wasn't broken. And then I formed it to the complete finished stake height that I was expecting. And I know that the lamp turned on because InfraStake has current monitoring on all of the lamps. So I know the lamp turned on. I know I had a boss to start with, and I don't have a boss now. That basically tells you, yes, I've staked it. So if you've done the validation to know that the strength out of that boss is what you need because you've done tensile testing or other forms of testing to verify the quality of your parts, then in your machine, every single cycle, by monitoring some of these very simple parameters, you can know you're getting good parts because all of those things are adding up to a good part. I hope that answers your question. A couple example applications for nanoSTAKE.
Yeah, so this is an automotive component. We've got, 9 bosses around this entire assembly. This was all staked in one press action using 9 nanoSTAKE modules. You can see we've got pretty decent cycle time here, 9.5 to heat and form, followed by 7 seconds of cooling time. So we're under 20 seconds to do 9 bosses around this entire assembly. So here's a lighting application. We've got 4 bosses, 1 in each corner of this kind of square cutout. Again, we were able to stake these in one press action. And the common theme to both of these applications is that it's a kind of a tight space down in here that wouldn't work with even our smallest InfraStake module. So that's where we leaned in heavily on nanoSTAKE to stake these. Finally, so we have a medical device here. This is a flapper valve. You can see the stake. It's not that easy to see. It's right in the middle. It looks so clean and clear. It's hard to see, but
like a molded component.
Yep.
Yeah.
But so that was staked with nanoSTAKE as well, and that was held to a pretty tight process control. To stake these once it was put into production.
Was this pretty flexible? Like, was this component flexible?
Nope.
No.
No.
Okay.
The flapper valve itself, but
so it bends up here and bends down here.
Yep.
Okay. Can you see my mouse when I'm doing that?
I can.
Barely.
Okay. Yeah, it's real small.
Won't worry about it now. One of the questions just asked by Guillermo is this suitable for flexible materials? I would say both of them can.
Yeah. Yep. Trying to think what we could do like a santoprene type of material.
Yep.
Something like that.
There's kind of 2 things. You can have if your boss is part of something flexible. We've had applications where that's the case and you're staking it. Kind of ignore that. I mean, this is showing bad boss angles and a bad joint design, but look over here on the best side. And so here's my boss, and this is the yellow is showing my mating component. If the blue is a flexible material and you form this into a stake, well, the stake head is also going to be sort of flexible. So it probably won't be a very strong joint. The other way around would be if the yellow, the mating component, is something that's flexible. And we've done that with like things like gap hiders, that flexible material that might be around the shifter or around the steering column inside of a vehicle. And there's other situations where you might have something that's fairly flexible. There, because the material itself is maybe kind of soft and easy to tear, there to get a good strength, what we typically want to do is take your stake head and spread it really far so that the flexible hole in the mating component can't stretch around the boss head. And so, but in both technologies, yes, you should be able to stake flexible materials. It's just you're kind of limited as far as how strong they're going to be. It is now 3 minutes past, and we thank you all for joining. If you have any further questions that you'd like us to address, please feel free to respond to the email that you'll get. Everybody will get an email that includes the recording of the webinar, a PDF of the webinar. I'm going to include the plastic welding decision matrix. And if you have specific applications that you want to talk about, or you want to send us some data and you want us to take a look at it, please respond to that email and let us know, because we are happy to help. If you are interested in getting more of this type of education by maybe having us come into your company and come to your facility and train your people, you can let us know that as well. We do lunch and learns on a pretty regular basis, and we do our best to tailor those to you and to what you want to learn. Once again, thank you everybody for joining. I hope you have a great rest of your day, and we'll see you next time.
Thanks, everybody.